Hold on, friends, because this is a very long video. Since this calculation has a lot of moving pieces, and since I want to set you up for tackling more difficult things later in the term, this video ended up long. Keep in mind that you can always pause it when it starts putting you to sleep. We're in the empirical formula section of our course, which is probably a great indication that we're solving for the empirical formula. That said, it's a good idea to get in the habit of pulling apart any problems you're given so that there aren't surprises once you begin calculating. Carefully reading a question and reorganizing the information in it is actually a very hard skill to develop well. If that's all I teach you by the end of the term, I'll be the happiest chemistry teacher in all the land. You might accidentally learn chemistry along the way as well, and that will be a bonus to me. All right, let's begin carefully reading. Our question starts with the word determine. So we should anticipate that whatever comes after this is going to be the unknown that we solve for. And lo and behold, the rest of the sentence tells us that we should determine the empirical formula. Now, I'm not content to have just read that though, because if I happen to forget what I'm solving for later, I'll have to reread the whole question. It's actually quicker to write the information over now so that it's easily reviewable later. Let's keep going. The next few words are information, but they're not key to my calculation. If we're solving for the empirical formula, of course we have a compound. And in this class, we're really always going to use elemental analysis data, so that part of our sentence is redundant. I'm just going to mark this whole thing out. This lets me know that I've looked at this part and I've decided that it isn't relevant to me. Moving on, I'm going to reorganize the elemental analysis that is given in the problem vertically instead of horizontally because that's how we math. We know that 52.2% of the sample is carbon, so I'm going to jot that down. We also know that 13% of the sample is hydrogen, so I'm going to jot that down. And we finish the problem off with the words, the remainder is oxygen. The remainder isn't a number, but it is a clue of how to get a number that I can use. So I've reorganized things. Look at us go. Remember that your empirical formula is a chemical formula in terms of the smallest whole number ratio of the atoms present in that compound. Lots of times, your problems will list the atoms in the order they should appear in the formula, but not always. If you have elemental analysis data for an ionic compound, then you will use the rules for ionic compounds when ordering your atoms, cation first, anion second. Even if one of your ions is polyatomic, there is still only one way to write these as each polyatomic ion has a unique, unchanging formula. You'll see a lot more organic compounds than you will salts here though, and that's because a lot of our molecules can share an empirical formula, and this idea is more important to this group of organic compounds. If you have a problem that involves carbon, hydrogen, and other atoms, then you will list your formula carbon first, then hydrogen second, then whatever else. The whatever else has to be the most electronegative or the closest to fluorine, and it should go at the very end. So if you have 4 or more atoms, they should go carbon, then hydrogen, then whatever is furthest from fluorine, and then whatever is closest to fluorine, like this. Here I have generic number signs because our job for these problems is actually to figure out what those subscripts should be. With the exception of single atoms, we're going to replace all of these number signs with a value, specifically a molar value. A chemical formula is, after all, just a molar ratio of all of the atoms present in a compound. Back to our specific problem. We've made some decent progress, but right now we're missing a value and we can't really use the other ones we have because they're in the wrong unit. So let's tackle the missing value first. We're dealing with percentages. And this won't be the only time we work with percentages in this course, and every time we do work with them, the individual pieces of our puzzle will have to add to 100% every time, all of the times, which is a great thing to remember because it allows us to work backwards if need be, and here we need be. Assume that this rectangle represents 100%. We know that 52.2% of that sample happens to be carbon, so just over half of our 100% would be attributed to carbon. We also know that 13% of our sample is attributed to hydrogen. Lastly, we know that this whole remainder of the sample is attributed to oxygen. In math terms, we can translate the remainder into the whole, which is 100%, minus all of the parts that we do know, which in this case are 52.2% and 13%. So oxygen is no longer an unknown and instead ends up being 34.8%. This isn't the last place we will see percentages this term, like I said, and for our purposes, they really do always add up to 100%. Let's say for a second that instead of our old friend 100% rectangle, we meet a new friend who we name 100-gram rectangle. If we keep the quantities of our three atoms in the same proportions, then it turns out that they will take up the same amount of our rectangle, whether we claim we have 100% as our total or 100 grams as our total. You're saying, great, but what a dumb thing to bring up. Au contraire, mon frère. Assuming that we have a 100-gram sample is the big trick that we need to more easily complete these empirical formula problems. Assuming that we have a 100-gram sample allows us to directly convert our percentage values to mass values, which is great because since we know our chemical formulas are mole ratios, we need to work towards all of our atoms being in terms of moles. And we have a conversion factor from mass to moles, but we don't have a conversion factor from percentage to moles. Now, some problems don't start with percent composition data, and this assumption becomes less important because you have to take other steps to get towards moles. But this will be our plan for any problems like these. At this point, my data table looks like this. This is progress since I'm in grams, but I can't compare the mass of one type of sample to the mass of another type of sample. This is because there will be more or less atoms in one sample than another, because the overwhelming majority of my samples will all have different molar masses. But some good news, by definition, 1 mole of something has to contain the same number of atoms as 1 mole of something else. So the mole is an excellent comparison between two samples here. It's also not a difficult calculation if we happen to have masses and a periodic table available. So lucky us. Our job now will be to move from these values in grams that we can't use as a comparison to values in moles, which we can use as a comparison. This is the same calculation that we performed in section 1.4. For carbon, we end up with 4.35 moles of carbon. For hydrogen, we end up with 12.88 moles of hydrogen. And for oxygen, we end up with 2.18 moles of oxygen. Though we've come up with values that we can compare to other values, there aren't really in a useful form yet, as we won't include fractions or decimal places in chemical formulas. So we have to keep going with our calculation. Our first step to getting the ratio into whole number form is dividing all of these values we just calculated by the very smallest one. This practice will always give us at least one whole number, and if we're lucky, all of our values will at least round to whole numbers. In this case, the smallest mole value belongs to oxygen, so any number divided by itself will equal 1. So, one whole number down. While we do a ton of little individual steps, it's important to remember that this is really one larger calculation. So what we do to one part of our equation, we have to do to all of the other parts of the equation. This means that we also need to divide our mole value for carbon by 2.18 and our mole value for hydrogen by 2.18. Luckily, these two calculations leave us with whole numbers. If you're determining the chemical formula for a molecule that includes carbon and hydrogen, they're going to go first in your formula. After the carbon and hydrogen, you'll list anything that remains in order of increasing electronegativity, or, in other words, put those furthest from the fluorine in front of those that are closest to the fluorine. At most, you'll have 4 elements to place in a formula, so you're really only going to have to prioritize 2 of your atoms. The mole values you just calculated are actually the subscripts we need to complete our formula here. We calculated that there should be 2 carbon atoms, 6 hydrogen atoms, and a single oxygen atom. Remember that the 1 is implied for oxygen, so we will not add it in.